Hey, thanks everybody for coming. I know it's a Friday morning. It's a relatively quiet day. You've been to most of these sessions by now, but just in case, we have a code of conduct. By agreeing to show up for this meeting, you've implicitly agreed to this. Essentially, the goal is to just be nice to each other. And if you see somebody with the yellow or green stickers, just make sure that you respect their preferences, as well as keep an eye out on the social battery pin if they have one. And yes, masks are optional, but highly recommended. And for virtual participants here, please stay muted unless you're speaking. And if you have any questions, just post on Slack. The Zoom chat is not going to be monitored as much. And we'd prefer to keep a record of all the discussions. So please use the Slack and not Zoom. And if you like to unmute and ask a question yourself, just make sure that you raise your hand and one of us, Jim or I, will ask you to unmute you, and you can ask your question. We have a relatively light agenda, and we are hoping there would be more time for discussion and questions as these breakouts normally happen to have. So on the agenda, we just have a brief introduction by Jim. I will talk about the idea behind cell-based cohorts and what the current status is. We have Matt Becker online, who's going to talk about meta-calibration and meta-detection. And then we'll talk a little bit more about what you should expect out of the data products from Rubin Science Pipelines, and we'll open it up for discussion. So with that, I'll ask Jim to take over.
Alrighty, so I'm starting off with a slide that these are already showed in another session that we love to show, saying that basically all of our plans from the algorithms workshop from just before the pandemic started are still broadly accurate. There aren't any major changes here, and what's changed is the status. For weak lensing in particular, what's really changed is that while what we're going to do has always been our plan, those plans are really solidified, and we can now talk about them in much more sort of formal and direct ways than we have in the past. These are the talks at the algorithms workshop that were relevant for this session here. So to remind you what DM's role in shear measurement is, and has been for a long time, the idea has been that we run a community vetted algorithm that we did not develop ourselves, one that has been well tested outside, and provide the catalog from that as part of our data releases. We're not trying to provide calibrated shears, because that often requires simulations and a lot of expertise that we don't want to try to have. But we do want to make sure that what we provide is calibratable, or doesn't need calibration ideally. So this has always been a big collaboration between DM and DESC, with DESC doing, I think, the bulk of the work, and DM, trying to absorb that and integrate it however we can. So during commissioning, we're going to do some basic null tests, and to make sure that the observatory and the processing pipelines are capable of doing lensing, at an initial level, but the real validation is going to happen later, or in concert at the same time with science collaborations like DESC. So a part of this is PSF modeling that we're not going to really dwell on in the rest of this session, but it's worth bringing up because PSF modeling is very important for lensing. It's of course very important for lots of other science cases as well. The main thing that we've done with PSF is that we've adopted integrated PIF. PIF is a third-party algorithm that's been developed by people in DES and DESC, hi Mike. And it's got lots of advantages over the PSFX code that we were using before. We are actually still using PSFX in alert production and for the initial steps because it's good enough and it's fast. PIF is a little bit slower, but we don't care about that at the stage that we care about getting the highest quality PSF models. It's modular and Pythonic. It's developed by people we know and interact with. And I think that's the biggest thing for me, is that we want to make sure that as PIF gets better, we can pick up the state of the art as it improves without having to go through a lot of trouble every time the state of the art improves. It can do chromatic and full focal plane PSF models, and has in production in places outside of our pipelines. We have not done chromatic PSF models. We do expect that we will have to do PSF models chromatic PSF models. I'm not sure that we'll have to do full focal plane PSF models early in the survey. It'd be really cool if we could, and it's a nice way to do chromatic PSF models. But my guess is we'll just do some simpler chromatic PSF models early in the survey. This is something we've mostly deferred doing until we have the real data from the real camera, because it's something that you have to have, I think, DCR to really try to understand well. And while we have DECAM data that has DCR in it, we don't understand the DECAM data as well as we understand the HSC data, and HSC data doesn't have DECAM in it. So this is one of those things where it just makes more sense to not put a whole lot of effort in until we have data from the real instrument. That does mean it's going to be a big crunch when we have data from the real instrument. If you've been around for a long time, you may have heard of the idea of multifit. This is how we said we were going to do shear estimation 10 years ago, back when CFHT lens was the state of the art, and it seemed like that's the way everything was going. I'm happy to say that we've done a lot of work to, I think, show that we don't have to do this anymore. Even back then, there were some hints that you didn't have to, starting with James D. And I think there's been a paper that a few of us wrote in DESC, led by Rachel Mandelbaum and Mike, to really show rigorously when you can and can't co-add and get a well-defined PSF out. So that's what we're going to do. We're going to make sure we make careful co-adds that we can do shear estimation on. As many of you know, we've been using the LSST pipelines as the HSC pipelines, and HSC is another major stage 3 survey. And we've been doing that with the HSM regaussianization algorithm, which is a very old algorithm at this point. It's not what anyone would consider state of the art, but the HSC people have done a really careful job of calibrating it with simulations, and they were able to get really good science out of it. We're going to continue to run regaussianization as well, because it's easy and it's fast and it doesn't cost us much. It's also pretty simple to use, as long as you do make that effort to do simulations at the level of fidelity you need for your science. The thing that we've been talking about for a while that I can now say much more formally is that we're going to run metadetection. The data products definition document is our formal declaration of what we're going to do in terms of being the document that's readable by scientists. It now talks about metadetection, what its outputs will look like in our catalogs, not in an exact scheme in the sense you're not going to get the exact same catalog, but you'll get a rough sense of what it would look like to work with this data and these processing outputs. So as I said, this will run on carefully constructed coads. Arun's going to talk about that starting in the next slide. It works by deconvolving the PSF, applying a small shear, reconvolving the PSF, and doing this repeatedly to get essentially the derivative of the shear with respect to the measurement, or the derivative of your measurement with respect to the shear that was applied. And Matt Becker will talk about that in much more detail in the talk after Arun's. All right, so I'll hand it off to Arun. I think I won't do any questions right now, because there's a good chance all the things I brought up will be answered better already by the people.
Thanks, Tim, for the introduction. So I'll talk briefly about how we construct the so-called carefully constructed coad or coadded images. The reason why this needs to be carefully constructed is, by this point in time, either from Aaron's talk yesterday, the keynote talk, or if you've been to Slack and see the camera, how it looks like. That's the focal plane with multiple CCDs. And those CCD chips individually, they have gaps in them. So what this means is that if you try to stack them all up to combine a single coadded image, you're going to have those chip gaps in those images. So this is a cartoonish coad, just focusing on where the edges occur. And if I have to highlight where the chip gaps are, the teal color regions here show chips gaps arising from one specific single visit image that went in there. And then there are another set of chip gaps from a different set of visits, and so on. So the chip gaps are an issue because even if you have a continuous PSF model along the full focal plane, the number of visits or the sets of visits that go at that particular point in the teal images, they differ from the rest of the images on either side of them, which means even if you had a continuous PSF on the focal plane, because you have different set of visits, the PSFs are going to be necessarily discontinuous at those gaps. Chip gaps are one of the primary examples. There will be similar discontinuities if you decide to mask pixels and not use them, or for some other reasons as well. So I could illustrate the chip gaps here for just 5 visits stacking to form a coad images. It's already looking a bit cumbersome if I have 10 images going in here. At least the saving grace here is that the edges seem to be parallel to each other. So one could potentially think of like having some regions where the PSFs can be continuous, some regular regions where PSFs are continuous. But once we move to LSST, because of the camera rotations, these edges are not going to be parallel to each other. They're going to crisscross each other. They're going to be some arbitrarily shaped polygons where the PSFs can be considered to be continuous. And it's going to be a much harder bookkeeping problem to see where the discontinuities occur, how do we handle them, and so on. And this is an issue because for objects that lie at the edges of these or that lie at the edges on these lines, that means there is no well-defined PSF for that object, which means you can't deconvolve by a single PSF, you can't measure shear, or you can't measure any properties of that galaxy for which you need to know the PSF well enough. That's because the PSF really does not exist. So how do we plan to handle this? So this is an idea that is also being tested in DES, and we've shown in some simulations that this works. So this is what we call as cell-based coads. The basic idea here is to predefine some cells or some regions on the sky and guarantee that for images of that particular region, the PSF is continuous. And if it is small enough, and if the spatial variation of the PSF is slow, then we can even assume that the PSF is spatially constant within that cell. And we construct co-added images just on that particular small cell at one time, and then we tile the whole sky with those small cells. So we can construct multiple cell coads, so as to speak. If you heard Yusra mention this at the updates science pipelines breakout, she refers to it as small cell edgeless coads. There are various adjectives that can go with it. We just call it cell coads or cell-based coads here. So this gives us a good handle on the PSFs. The main disadvantage here is that you lose some amount of signal to noise ratio. I'll come back to that in a second. But there are a lot of advantages from systematic sense. So because most of the covariance or correlation in the noise is introduced in the warping stage, taking a single visit image and converting them to a common coad coordinate frame. The noise is roughly stationary, and you can characterize it well by a correlation matrix. We are actually looking forward to this because this means that we can keep better track of uncertainties in, say, flux estimates or shape estimates. And we've historically known that galaxy color uncertainties are underestimated. Looking at Eli, who's been complaining about this for a long time now. And we're hoping that tracking the correlations properly is going to help us improve that. And the PSF is continuous within the cell, and Matt Becker, who's going to speak next, and Aaron Sheldon, Bob Armstrong, they've also shown that we can actually treat it to be spatially constant within the cells, which means that instead of evaluating the PSF on the fly at every single location on demand, we can actually pre-compute those PSFs and save them with the coordinate images. This is going to be a huge time saver because one of the more expensive parts is actually just evaluating the coordinate cells at the center of various galaxies. And because the image or the coad itself is well characterized, simulating images for shear calibration or any other purpose becomes a bit easier. Yeah.
Why can you store them here, but you couldn't store them even if they were gaps? That's the point about why is this particular line stored?
Because there would be many. So if we were to store the PSFs on the coordinate images, then for each single polygon here, we'll need to store them. And yes, yeah. So more complicated data structure. It will also require a lot more PSF images to be stored as opposed to fewer ones based on how we define cells. And sorry, and for people in the audience, Chris' question was, why can't we store PSFs even on the regular coads? And the answer there was that we could in principle, but then we'll have to store it for every single polygon there. It's much harder.
One other basic question. Is the PSF only?
I apologize. So one other basic question, in terms of what you're storing, do you only store the PSF for the coad? Is it only defined for the coad, or do you have the PSF also for the individual exposures, calibrated exposures that were part of that area?
So the way we currently do is the PSFs for the individual single visit calibrated images are stored with the images. We just compute the PSF for the coad on the fly. So we go back to the single visit images that contributed to a particular pixel in cell, and then we use the same ways that we use for co-adding images, and then we do that for the PSF and compute it on demand.
So to clarify, when we talk about the PSF of a single epic image, it's a PIF object that's like a black box that you have to ask it for the PSF image at a point or something else. When we talk about the PSF of the coad, now it's a you give me the cell and there's an actual image saved. So it's a simpler data structure that doesn't require you to understand what interpolate or whatever PIF used. So it's not quite apples to apples when we say PSF there, but you get a PSF either way. Because we approximate it as constant over the scale of a cell.
Right. I think probably better would be to also have the first two derivatives, right? Like the gradient. It's like basically 3 images.
Yeah, and that's not out of the question. I certainly expect us to eventually store the derivative or some derivatives with respect to color of some kind.
Maybe, yeah, color too, maybe. But I think it's, locally constant across the cell is probably not a great approximation, but locally linear is probably a very, very good approximation.
Yeah, I think it trades off with the size of the cell, and I don't have a good sense for the cell size we've chosen right now, which whether you need the extra terms or not.
Right.
You could always shrink the shell, or you could grow the cell and add derivatives.
We haven't done the linear thing in DES either, but it's been sort of obvious in my head that that's the better way to go.
Okay.
And because I think you can do all the meta detect functionality with a linear based one, but that requires coding,
yeah,
which nobody's done yet. But I think that's likely where we may end up.
Okay.
So to follow up Mike's point, so are you saying that we can still do meta detection, which is coming next, even if the PSF is not spatially constant, like some kind of an averaged one? Yeah. Okay. Tony.
Yeah. So this is a good idea, I think. There's something called SFIT that we had once, which was a little different, also worked, but then with the PSF had to be known everywhere, and it was discontinuous, of course, across the boundary. So the thing I worry about, though, is that these cells are all going to end up having a different sky level, and there's going to be a fair amount of variance in sky, I think, from cell to cell, and that means that that's going to print straight through to covariance problems in the cosmological results.
You can think about the sky as being a thing that is astrophysical, that is constant on all of your frames, and you can as a component that's not that's different on every single frame. And we really want to get, for many reasons, not just this one, get the one that's not constant on all the frames out of the background in the individual single epic images. Because once you've co-added it, you've made it much harder to subtract that background.
Yeah.
Now, there's still going to be an astrophysical background, but that should be the same in all of those images. Except like really higher order things like it being chromatic and you've got a slightly different effective bandpass in each one. And we've also got some ideas on how we can subtract that background when we're doing the co-adding by making sure that not with these coads, but with the other kinds of coads we've got, you could do background matching and essentially make sure that the background of all the images except one, gets canceled out as a result.
Yeah, so you try to connect all of the cells across the image. I mean, I'm thinking of Kelvin et al. All right. So
yeah.
There's going to be some serious problems there, estimating the sky level.
Yeah.
Okay. I see Eric first and then Eli.
I guess the question is just down the road, how much monitoring code do you have to see if you're putting power in at the coad scale, at the cell scale? In, you know, whatever science quantities you're interested in.
That would, I mean, that's something that's on my mind, but I think it's, yeah, like you said, it's down the road. Like, are you expecting if we compute a correlation function, there would be like some peak on the cell size scales? Or?
Well, that's, I mean, if you artificially analyze your data in blocks of a particular scale, the first thing you should do is check down the road to see if you've artificially inserted power into any physical quantity at that particular scale, right?
Yeah, so my first thought was that I think repeat what Mike said is it's a very small scale compared to the ones we care about for weak lensing.
Yeah.
The other thing I'd say is that this is the kind of question that I would definitely defer to Matt and Aaron and the other DESC experts. I'm hoping they have an answer for this that's more than just we don't care about that scale, or they'll tell us that that's enough.
And just for reference, we are talking about one Archimedes scale. So that's something typically too small for like cosmological analysis. Sure, yeah. 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 No, agree. Eli.
Yeah, one other thing that I wanted to add in, I mean, there is the challenge, not just of the sky, but the noise of each cell is going to be different because they're different depths, and that's Matt and Aaron might have something to say about that. But I mean, but you're trading there, a well-defined but patchy noise to a very ill-defined crazy pattern. But on the other thing, another advantage of the cells that I wanted to highlight is to know what the transmission function is of your coad, for chromatic corrections down the stream. The cells make this, and with co-adding the PSF is a problem. And then co-adding the transmission function is also a problem over all wavelengths. And now you have one well-defined transmission function in each cell. And so that makes these operations a lot easier.
Yeah. So I guess one sort of sleazy way to answer Eric's question that I'm not super happy with, because it raises the specter of maybe you should do multi-fed after all, is that all of these problems with the cell-based coads are present in the not cell-based coads. It's just that you don't know where the boundaries are. But it's also true that we're assuming that that's enough to make it work. And at LSST depth, it's also true that while you get boundaries everywhere, and it's nice to grid those up with cells, you've got so many epochs with LSST that the actual differences from cell to cell is going to be pretty small. Because if you drop one epoch out of 20, it's not nearly as big of a deal as if you drop one epoch out of 5. Yes.
Yeah, I figured Matt might
Watch
have
Matt's running commentaries. You've got your laptop out.
Do you have any other questions or comments online? Okay. If not, I'll move along. Okay. So yeah, and I think a lot of things came up. I'll also show some images of how the noise looks like and the things, but let me start with some cartoon here. So if we take some projection of the sky, the red dots here are actually like what we call as tracts in data management land. That's the region where we approximate WCS to be the same everywhere, so on the tangent plane. And that's a zoom in version on the right that shows how the tracts kind of overlap with each other. We further divide tracts into what we call as patches because they are more amenable for the amount of data that we can handle and process. And we are proposing to further split that or partition that into cells. So on the left, this one entire green rhombus kind of a shape, that would be a patch. And the semi-transparent ones there are different single visit images that at least partially overlap this particular patch. The different colors show you what the different single visit images are. And if we zoom in further on the right, then you can begin to see how the cells look like on the sky On images, they are rectangles or they're squares, but on the sky, they're kind of warped. But that's all right. And what we are proposing here is that we include a visit only if it completely overlaps the cell. And if it has a partial overlap with the cell, we don't include that. What we are, this sometimes raises questions. So just to say, we're not proposing to throw away an entire visit, then we would not have like any visits to actually coad. What we are saying is that we'll throw away some parts or some pixels from some visits, and we will not use that in the coordinate images, but you'll use a different part of the same visit to coordinate in different regions of the cell. So how does this actually avoid edges? Well, it doesn't. It still has the PSF discontinuity at regular intervals. It just makes it easier to track. And what that still means is that for objects that fall on those regular edges, the PSFs would still be ill-defined. So what we can't do is to just have cells that don't overlap and just tile the sky. We need to have some buffers so that if an object falls in the edges, we can still go back to the individual cells and find a region where that object exists with a well-defined PSF. An object can exist in two different cells completely as well, but we can track that better than, or that's a better problem to handle than having objects at an edges with ill-defined PSFs. Yes, going more into the cartoon picture of how the buffers look like. So this is the tiling made by Eli here about 2 years ago now. So what you're seeing here is a patch divided into cells with inner and outer buffer or boundaries. And on the right, you just see a zoom in of the lower left corner here. The blue line that you see is what we call as an inner region of the tract, and the teal that you see is the outer region. And here are individual cells that go in here. The darker teal region is the inner region of the cell with a lighter outer buffer. And these tile so that there is still overlap between two cells. And we'll cover the entire patch and then the entire tract and so on. So I raised the issue of that potential, or not just potential, I think it was sort of evident that there's going to be loss of signal to noise ratio. This is work done by Bob Armstrong, where he analyzed how, as a function of the size of the cell, you would lose the number of visits that go into a cell, and thereby the loss to signal to noise ratio here. So the smaller the cell is, the lower the chances of there being an edge, which means you can have maximum signal to noise ratio if you go for extremely small cells. But then you can't go arbitrarily small, because you need to at least have the cells typical or slightly larger than some of the blended sources or blended objects that you should expect. So this is why we can't go arbitrarily small, and we've chosen something around 1 arc minute. This is not final. This is always configurable, but right now we're sticking with about 1 arc minute. And what the plots on the center and right show is, if you had a smaller cell, say about 0.1 arc minutes, then you probably lose only about less than 5% of the visits. And that in terms of phi sigma depth comes to be about 0.05. And if you go all the way to 0.8 arc minutes, then you lose about 20% of the visits. And in terms of phi sigma depth, you probably lose about 0.1 or 0.15 magnitudes. Again, we still think this is a good trade-off for the better PSF or better, in general, better systematics controls that we can have with cell-based coads. But if you don't care about PSFs, if you just need the deepest possible images, you can always make the coad, or there would be one version of the coad where we would have not excluded these partial visits, and that would be available if all you care about is deep imaging. That's not systematics limited.
We've got a question on Slack
Yeah.
from Dan, but what the point of the buffer overlap regions, and I want to emphasize that there's sort of two ways of analyzing these cells. One, you can do processing cell by cell, including the whole overlap region of that cell. And once you've done that processing, you have to resolve the duplicates from the neighboring cells in your catalog at catalog level or something like that. The other alternative is that you can stitch the cells back together and essentially throw away the overlap regions or use the overlap regions to like homogenize your PSF so you get something nice and smooth. There's lots of ways to use these, but you want the overlap regions to be at least the size of the PSF and ideally the size of the typical object you care about. And of course, as you get really large objects, some of them won't fit, but that's okay because if you have really large objects, then the effect of the PSF on that object becomes small and it's okay as well.
Yeah, so the hardest thing is to remove the duplicates in a way that doesn't screw up the metadetection, careful shear calibration stuff. And Matt and Aaron have been thinking about that for a long time. So I think they have schemes, but that's the tricky part.
Thanks. For deep blending and communication issues and all of this, it can be proved that any object that is half the size of the overlap region will be uniquely measured, and anything that is larger than that can have differences depending on which side it goes on. Yeah, and I did this proof years ago and now I can't remember it. Oh no, in the overlap region. So it's
on the mic. Eli on the mic.
So I'll say my concern first and then Eli can respond. So I think in the overlap region, if you get the same thing measured twice, they're not guaranteed to be the same answer in both places because the PSFs can be different because of how the different things that went into those two cells.
The measurements won't be, but the positions, I think. I don't know, maybe not. Maybe I am wrong with the different PSFs. Yeah.
Tony, have you tried this? Has this been tested on data that you believe?
This is being tested in DESC Y6 and we have like some prototype ones for the Rubin Science Pipelines, but yeah, we have plans of doing this in HSC.
So what I'd like to see is a bake-off between SFIT and this, because SFIT is actually more simple. And you have, so you have two catalogs. You have your galaxies and you have your stars. And the stars are measured everywhere except right on the very edge of a region. And so it's a much simpler approach. And I think it's less bandwidth than, I'd just like to see a bake-off between the two.
Would that be on single visit images on coads? Because it.
So in forming a coad, the way SFIT works is that you know all of the components that went into the coad for your galaxies. The shears, of course, are compromised because the PSF is different in different patches. But then you also have a separate catalog of all the stars that have been run through. And because you know the PSF inside of these big regions, these regions are large. And the PSF can vary across the region because you know that too. And so then in forming the coad, you can deconvolve, or better yet, convolve and marginalize. And it's ended up being very simple and pretty reproducible on data that we knew the true answer on.
So, Tony, my recollection of how this works is a little bit, is very old now. But my understanding was it was essentially you were making postage stamp catalogs of every galaxy and building the PSF for that. And that meant that if you had two galaxies next to each other and the discontinuity between them, you would get different postage stamps, there because of the different epochs contributing. And that would work as well as the cells. I think you just end up co-adding many more pixels altogether than the cells. Is that right?
That was multi-fit. SFIT is a whole lot simpler.
But where do the discontinuities go then?
The discontinuity occurs right on the edge of a CCD, or better, the edge of an exposure.
Right, but that's the same ones, those are the same discontinuities we show. And I think
Right.
my understanding is that that sort of approach works fine if you've got a small number of epochs. But when you have LSST numbers of epochs, then you don't have large regions anymore. And I think that's why we're still forced into this and why we got away without it for HSC where we've got 4 or 5 epochs.
Yeah. I'd like to see this trade written up or tested. That's an interesting idea. But we had 40 images. Well, it's only a factor of 3 away from LSST.
Yeah, 40 would be enough to cause problems, I think. Yeah.
But yeah, I think the real test is going to be from DES Y6 analysis. While we passed, any more questions online, Jim? Anything on Zoom or Slack? Okay. Okay, so I've been showing a bunch of cartoons. Here are some cells. This is base cells or cell cohorts made from DC2 images. I've just picked 4 adjacent cells here. And you can see the overlapping regions. I'm just highlighting various structures that you see repeating across the cells here. So you can see this particular galaxy that occurs in the top right buffer for one particular image, but in the interior of the other image. And then here are some other structures just to guide your eye. So the eventual goal is to just take these cells individually, process them or run measurements on them independently, and then do a catalog level combination. And when we are running shear estimation algorithms, they would work only on these cells, and then again do catalog level operations to reject the duplicates. And Jim mentioned this earlier. We don't necessarily have to just work on this individual cells. If you'd rather work on the normal path scale code, you can stitch them back so that you don't have these overlapping buffers. The interior region of the cells don't overlap, and you can recover a path size cohort. In the limit that there were no edges, or if you decide to not throw away any single visit images that partially overlap, this cohort would be exactly the same cohort that you would have otherwise produced without going through the whole cell-based procedure. But this particular one is stitched from cell-based cohorts. I'm just pointing to this particular region from the cohort where you can clearly see that there is a change in the noise profile because the number of visits were different. I think one is much shallower than the other. And if I remove the boundary box here, the cell boundaries are very clear. This is not just one cell here in this one. I think this is probably about 3 cells here, but you can see the clear change in the noise profile. What is still surprising to me, I still don't think, I still have to convince myself that apart from these very few regions, the cells otherwise, or the stitched core still otherwise looks pretty homogeneous. There doesn't seem to be this kind of discontinuities in the noise profile or in the PSF. But this is probably one of the worst case one.
How many single effects went into that?
I don't remember the number off the top of my hand. It's probably about 10 to 20, I think, but I have to double check. Mike's question was how many single epoch images went into this. This is DC2. Yeah, 20-ish, yeah. Okay, I think that was all the slides that I had. I will leave it to Matt Becker to talk more about the exact shear estimation algorithm itself. Matt, do you want to share screen or do you want me to change slides?
Probably be faster if you change them and
Okay.
I'll just say
Okay,
the next
then
slide. Okay, so yeah, I'm Matt from Argonne and I work in the LSST desk. Next slide, please. Okay, so we're going to talk about meta calibration and meta detection. I'm going to move fast because there's 20 minutes left in the session and I want to leave time for discussion. Basically, shear measurements for weak lensing work in the linear regime. This equation here is just the exact same thing that Jim said earlier, but written in equations. You expand out your observed shape G1 as a Taylor series in the true shear gamma 1. And this capital R thing is this first derivative at 0 shear, and that quantity is called the response. There's various names for this quantity mathematically in literature. We call it the response. So basically, the name of the game in these techniques is to figure out the response from the data itself using finite differences. And you have to include everything that depends on shear, the true shear, in the response when you compute it. So if you go to the next slide, please. So this is an example for meta calibration, from Eric Huff and Rachel and Aaron. I've only done a one-sided difference here. In actuality, it's a two-sided difference, but you see the idea. You deconvolve the PSF, you shear the image a little bit, you reconvolve, and then you compute this response. There's a bunch of other technical bits about what to do about sheared noise and things like that. I'm not going to cover here, but all of those are covered, in these two papers. And this has worked for isolated objects to LSST year 10 precision for a long time now. All right, next slide, please. For blended objects, the community's only recently discovered accurate techniques. And by accurate, I mean here something that you can just run on an image and get a shear that works at, better than part in 10 to the 3, which is about an LSST requirement. So for meta detection, essentially the backstory here is that in the dark energy survey year 3 analysis, there were persistent 3% biases in our meta calibration catalogs. And Aaron, Sheldon, and others did a bunch of looking, and they figured out the problem is object detection itself. So it turns out that when you leave detection out, you're computing the wrong response. And that's a really important point. Other people have verified these results. There are now very fancy methods from Rachel and Jane Chung that do all of this analytically and find similar conclusions. But the basic idea is that in order to measure shear at LSST precision without calibrating it in a simulation, you need to include the detection of the objects in the process in order to get the response. And the side effect here is that meta-detect will naturally measure the response of a full image to a constant shear at a single redshift. So next slide, please. Right, so here's how it works in pictures. The original image is here. This you can imagine being a cell coad or a larger image. You deconvolve the PSF, you shear it, you reconvolve. You do this for each of the possible different ways to do this. No shear, the different shears here. You run object detection and shape measurement on each of the images. And then you compute averages over the catalogs from each of the images separately. And then finally, you get the response of the image by doing this finite difference on the catalog averages. And this gives you a measurement of the shear in the image. Cell coads with meta detection recovers shear to better than 0.1% in simulations without calibration. And these simulations include a lot of the effects we're going to see in real data. So varying PSFs, pixel masking and interpolation, bright stars with bleeds, things like this. So it works really well. We treat the PSF as constant across the image. And if you just look at the empirical variation or variation in models of the PSF for LSST, this will be a good approximation, even for LSST year 10, in terms of being able to recover shear at this level. So there's no reason we have to treat PSF variation for cosmic shear if we don't want to. Chromatic variation is a totally different story. All right, next slide, please. So here's the schematic overview of the pipeline. So Arun just told you about all of the cell coadding. That happens in each band separately. And then all the bands, the cell coads in a single location in the sky are fed to the meta-detect pipeline, and it comes back with a combined shape from the bands you want for shear, plus a bunch of fluxes in the other bands, positions, other metadata, masks, things like that, telling you what happened essentially. So that's what the pipeline will give you. And all of that will appear in tables as described in the data definition document or whatever that's called. Next slide, please. Real cell coads are quite messy. So this is from some work I have in prep, been in prep too long, basically testing all these algorithms for DESC-like surveys. And what you can see here, I've included focal plane rotations, even though that doesn't happen in DESC. You can see all of the warping and all of the interpolation and masking of pixels and how all of that comes out. I'm not going to go through all of the details in this slide, but each row is a single epoch except for the bottom one, and you co-add down the columns. And so what you see is that the final data product will come with an image. It comes with a Monte Carlo noise realization, which you can use to do various things, including meta detection. You get some estimate of what happened to each pixel, so what fraction of each pixel ends up being interpolated, excuse me, and you get a PSF, a coad for the PSF. And these algorithms, we've carefully verified them. This was mainly Aaron, and it took a long time, but they work for LSST year 10 shear in simulations that look a lot like this. So we're pretty confident that this is going to be at least robust for year 1. All right, next slide, please. And then, as Arun has mentioned, we have a version of this working on DESC, which we're finishing up hopefully soon. And these are just some plots from the catalogs, just to show that they exist. Nothing really of interest here besides the plots. And I believe that's my last slide. Yep.
Yeah, give it back to Jim to talk more about the data products that we'll expect from the science pipelines. But yeah, there are questions.
Hey, Matt, this is Chris. So I'm a little confused. I thought I remembered when we had discussions about this before that because of the way this was done, there's something like 5 catalogs, one for every direction. And so
That's right.
here, because of the detection. And so here, I mean, here you're just showing a catalog and the final data product per filter, but really isn't it like 5 times that? And are you really going to make that available to the whole community? Is there going to be some sort of, I mean, we care about that, but that's going to confuse a lot of people. Is there going to be some catalog which is like this is the,
I think Jim is going to cover that in the next section anyway.
Yeah, I'll actually cover that shortly.
Yeah, but the short answer is that I should have said shear catalogs, but the only one that you use for science is the 0 shear one, and then the other ones are calibrations. My daughter's sick today, so that's the short answer to your question. So there are 5 catalogs for the entire survey, and you compute the response from 4 of them, and you compute your correlation functions from the 0.
So the point being, you do all of your cuts on all 5 of those catalogs, and you have to do that big division that Matt wrote up there after you've done all those cuts. So you have to do it on 5 of those catalogs.
Yeah, I didn't go into much of these details about how you use the catalogs, because it turns out when you want to do tomographic binning and a bunch of the other stuff you have to do to actually do a cosmic shear analysis, it gets pretty complicated pretty quickly. And those are things that, in many cases are still being worked out. But, that's the idea.
All right, so I'm going to talk a little bit about what this will look like in more detail and some of the remaining challenges for getting this integrated into the LSST pipelines. So we're going to run the DESC developed metadetection code essentially as part of our data release processing. We envision this being like they've got a Python 30 party package. We'll put it in our content environment and we'll use that and we'll import it. And when they cut a new release, we'll update our content environment, et cetera. I think for the cell-based co-addition code, it'll be more a matter of us integrating their code. We're going to take the low-level bits, change them not at all if we can get away with it, because as Matt said, they've already been very thoroughly validated. But we're going to have to add code around them to deal with complications that were not in those simulations. Mostly backgrounds, as I said in response to Tony's question, we might have to do some background modeling as part of co-addition. And so some of those background models may be a little bit late arriving. We've also got code that runs during co-addition, or at least compares warps to find artifacts and to find satellites. And so we're going to have to make sure the co-addition here is aware of that too. And so in many cases, that's going to be, we've got a new mask claim that just tells us we're going to have to reject more epochs. As Matt alluded to, you also, if you have a very small amount of missing pixels, you can interpolate over that every epoch rather than throwing away an entire epoch because you had a cosmic ray hit 5 of them. You just have to make a decision and validate that decision about how many bad pixels you can tolerate before you throw away an epoch over a cell. So there will be some refactoring of that coad code, but we want to make it sure it's as similar as possible to the current code that DESC has developed. And I think we want to make sure we've got tests and CI such that when DM sort of takes ownership of maintaining that code, that we can make sure that there are no changes we make that change what the coads look like. And therefore, if the coads are the same, then we don't have to worry about having to redo the shear estimation tests that Aaron and Matt have already done. All of DM's deep coads will be cell-based coads. They are not right now. but they will hopefully be the same as the metadetect coads. I think they'll certainly be produced by the same code. Maybe they'll be configured differently. I don't think we've identified any unreconcilable differences between what the DM deep coads should be and what metadetect coads want. It's possible something will rise. Matt or Mike, so you've got a.
Are you going to experiment with different sized coads? Because I could imagine there being science cases, not what we care about in here, but they would want the same kind of thing, cell-based coads, but on even maybe 10 arc minutes. I don't know if that's too big, 5 arc minutes or something. Because if you have a deep field, right, you're okay throwing away maybe even half of the images and get a really good coad that's big enough to do some of these bigger objects that people care about.
I think we'd considered it if someone brought us a science case, but I'm not aware of a case where people care about that level of PSF precision over large objects large enough for that to be useful.
Yeah, I can doing like type morphology of galaxies.
But I think I think it's more the, well,
if you want to resolve globular clusters in a galaxy, a big galaxy that has lots of interesting substructure, you want the PSF right to do the detailed studies of the outskirts of a galaxy.
Especially in strong lensing cases inside of those.
Yes, but I think that's you can also invert your measurement algorithm to do your fitting in a way that's aware of the cells. And I think that tends to be my preference for how to do things, but it does put more complexity in the people doing the science analysis. But I think it just
I would
better.
strongly consider that at least.
We have a limit on how many coads we can produce. I'll get to that, or at least how many we can save. So anyhow, yeah, metadetection is going to take advantage of the cell structure. There are a lot of other measurement algorithms that we run that it'd be nice to modify, and we're going to modify some of them to take advantage of that cell structure. There's a lot of them that don't care about the PSF at that level of detail. I think it's easy to think about how the PSFs vary a lot, even spatially, single epoch, and naively propagate that to the coads. But one of the things I've learned that Matt has intuition for that I didn't before I talked to him a lot about this, is that when you coad that many images, the PSFs actually average out quite a bit. So the discontinuities are really pretty subtle. And I think there are relatively few science cases that care about those subtleties and need to adopt what they're doing. Many of them can just use that stitched coad and deal with the discontinuities or ignore the discontinuities. As Arun said, that tracking the noise correlation matrix will get easier. Right now, we're not planning to have our image subtracting templates use cell-based coads. I don't think there's anything fundamentally wrong with that, and I think there's some intriguing ideas, but there's no evidence that we need to make better templates in this respect for image differencing. And since they've got their validation underway, I don't want to disrupt it by changing something they don't want changed right now. Certainly in future data releases, that's worth considering. We've talked about this, was Chris's question before. So the nature of metadetection means that you have to have a set of shear catalogs that's separate from the object catalog. You end up with 5 rows per detection instead of 1 row per detection. And in the DPDD, this is what's now called the shear object table. It's a different table from the main object table. If you join the shear object table back to the main object table to pick up a new photometry measurement, you blow up everything you just tried to do by making that metadetect table. And so the shear object table will have additional columns for photometry, PSF quality measurements, other bits of metadata, flag columns. It will be focused, or it's driven so far by the needs of cosmologically weak lensing. We're certainly open to including more columns there. It won't be as rich as all the measurements we run on the main object table. And I think maybe the big difference is that in the main object table, we can try to do the deblending to be as astrophysically good for any one object as we can. And for metadetect, we have to really try to make the deblending that we do something that we can differentiate, and that limits how well you can try to make it astrophysically good for any particular object. As I said before, if you need shapes of objects from the main object table, you can still use HSM for that. All right, here's a little screenshot of the DPDD. There's a whole section here you can read, but I think if, it's the text version of what we've been presenting today. What about other shear estimators? There's always new shear estimators coming up. There are some very exciting new ones that I think Matt alluded to, and others as well. I think if it's faster run, it involves a small number of new columns in one of those existing 2 tables, and it's easy to do. If it's slow or requires new rows or tables, because you need to do your own detections in a different way, which is I think the case of most of them these days, then it's harder for us to say, oh, we'll also do that. I think there are some candidates that we can certainly do in the future. I think it's probably a little bit late for us to try to get another one in for DR1, DR2. But every data release, we can reevaluate these decisions. We can maybe run another one. Maybe we'll find something else just outperforms metadetection. We won't run it anymore. But it's worth keeping in mind that there's going to be a long lead time for those kinds of decisions, because by the time when we're making a data release, we're just about time to start processing the next one. There's going to be a hard feature freeze. I mean, if we're certainly going to try to fix bugs that people find in our data releases, but it's often going to be, the 2 data releases later because it's already too late for the ones coming out next. The last thing I want to talk about here is that we do, by switching to these cell-based coads with their pretty large buffer regions and pretty small cells, we are increasing the amount of pixels we're storing with our coads. And I think we can tolerate this right now, but there is pressure to shrink that a little bit. And I don't want to go do that, unnecessarily. But if we're going to do another large validation run for some other reason, I would like to be able to push how much of that push the ratio of overlap cell to not overlap cell to try to shrink these a little bit. We're also going to be propagating a monocolored noise realization. This is part of dealing with that correlated noise and metadetection. It's also a very nice way for us to get our own checks on whether our uncertainty propagations are good, at least at a broad, coarse way. There's some other options for how we might be able to shrink the storage. I think in many cases, DM is the most lossy compression averse group because we've got lots of customers and we don't want to annoy any one of them. And it's hard to say that we won't if we do some lossy compression, but it's always worth thinking about. There may be some things here that we're producing for metadetection that we don't need to keep after metadetection, like the noise images, maybe even the buffer regions if we don't think people are going to run their own algorithms on buffer regions. And regenerating anything we discard is always possible, but it's usually expensive. And I think there may be some room for negotiations between DM and DESC, which I believe DESC wants to get all these coads over to NERSC. And we might be able to, get them over to NERSC and then discard them on the DM side and not have to store them long term.
So I can just, when you transfer them over to NERSC, I'm quite sure we can handle lossy compressed versions of them.
Okay. Yeah.
Shear doesn't really care about loss. It's way below the noise that we have on every galaxy already.
And that might open up the possibility if we had to make a metadetect coad that was different than the main deep coad, that might give us the option to retain the metadetect coad longer. All right, that's all I have. I think it's time for more questions and discussion. But we've had a lot so far. Tony.
You mentioned satellites. I can imagine 2 cases. And this is alluding to Erfan et al. Paper in progress. And that is the satellite trail is detected.
Mm-hmm.
In that case, what you want to do is to mask it out with a wide enough mask that you can't imagine having any problem at any useful surface brightness. And that actually ends up you end up losing a negligible number of pixels in the image that way, so it's not a big deal. But I just wonder if that prints through. The other case which worries us more is that nothing is perfect, and we are finding that satellites at different altitudes, different types of satellites, different orientations, have surface brightness profiles that are multi-peaked. And DM fails to detect those.
Okay.
Currently. Maybe there's some software that I don't know about, but it is not detecting them. And so,
I was
Michael.
just trying to understand what multi-peak meant.
Oh,
As
so if
it
you
were,
go-
you see 2 streaks in the image
Yeah,
then?
so if you go across the trail and map the surface brightness as a function of distance from the trail, it's not a single peak. If the satellite becomes large enough, there's a giant notch that's taken out of the middle, so it's 2 peaks. Or if it's, yeah. And this depends on seeing the whole, it's a messy, it depends about 10 parameters roughly that you can,
So
we know about.
my main thought on this is that it's at least orthogonal to these questions. I think no matter how you do the shear estimation, the satellites are going to affect it roughly the same way. Certainly, if you, I view satellites that you find as additional masks that I said that if it's a large enough mask region over a cell, then you throw away that epic cell combination. If it's a very small amount, maybe you can interpolate it. And For the undetected ones, it's the same sort of mitigations it would be for any other approach. You want rotational dithers, you want all kinds of dithers to mitigate how it prints through.
Yeah, but I mean, you're going to end up with one less image portion being added into your coad along
Yes,
the
and-
masked region, and that creates a little noise excess along. that.
Yes, so it's another case where certainly if you throw away the epochs, you lose a little bit more signal noise. And the fact that we're doing cells, and the way I think about the signal noise loss from doing cells is that you're essentially discretizing all of the boundaries on the cell size. And so if you think about your satellite mask, you end up discretizing that into a bunch of cells, and you use all the areas in the cells in that image, not just the part you would have ideally liked to mask.
So this works well if your cell is on the order or smaller than the
Right.
width of the
That's another
satellite
reason to keep your cells small.
mask. Okay.
Eric?
So at some point, I can't remember who, but somebody said that for the shear catalogs, you can't really run any deblender you want. You're stuck with. So how does this tie into the idea that you want to apply all your cuts on each of the shear catalogs before you calculate the shear essentially? Because I can easily imagine that when you're making tomographic bins, people are going to want to cut on the quality of the P of Z estimations, and they're certainly going to want to do that on the best deblended things they have.
I could make a guess at that, but I'm going to defer to Matt.
Yeah, so you just can't think that way anymore. So all of that's out. There are no individual P of Zs. There is nothing but what's in the meta-detect catalogs if that's what you're using. So if you want to make tomographic bins, you use the meta-detection fluxes. If you want to make a cut on an object, you use any column in the meta-detection catalogs. There is no way around it, and you can't match back to anything else. There's nothing left. That's what you have.
But that's
So
not
the
what I
way
was
we-
saying. Sorry, Matt, that's not what I was saying. I was saying in one of the shear catalogs, you're going to want to apply the cuts on the good P of Z, the objects that give you good P of Zs when you're deciding how to make the N of Z ensembles. And you're going to want to use the best estimate you have in that shear catalog. But
Okay.
if you're not allowed to do deblending in that shear catalog, then
You can't use it.
That's right. So you can only make your tomographic bins on photo Zs that are made from the Medi-Cal fluxes.
that I understand. But you've also gone
Well-
a step further and said
No,
you're
well,
not allowed to run complicated
It's not a step
deblending.
further because the Medi-Cal fluxes do not have deblending. They cannot have deblending.
Okay. So,
But the blending breaks the shear measurement.
Yeah.
So even if you got better photoz's, you would end up with a biased shear measurement. And it's not clear you're actually going to win anything cosmologically.
But
Yeah.
Matt, you are running some kind of deblending in that. I mean, you're not trying to run a really,
As
you're not
linear
trying
as
to deblend
possible.
everything, but you get better shear estimates. You do try to deblend a little bit, so you're not doing like intrinsic elliptic distribution that has wonky 5-armed things, right?
Well, whatever the detection algorithm is doing for you. And then we just take the detected positions and we run on them. So in the case of source extractor, it's whatever source extractor decides is different objects. We just run at their centers. So I don't know what exactly the DM detection algorithm looks like. I haven't looked at it in detail, but it's whatever centers the detection algorithm gets you is what we use. And this deblending thing it's a bit of a red herring. The exact statement is that of the deblenders we've tried so far, we couldn't find one that didn't break the shear. That doesn't mean one doesn't exist. It just means we haven't found it yet. So it could be that in the future, there could be a deblender that has the correct symmetries and no leakage in whatever that it makes the shear measurement work. This is just the state of affairs now.
so when people are putting effort into how to define the tomographic bins, the guidance that you're giving them is you can't use anything that's come from a deblender. You have to use things that come from. But,
Yep, correct.
okay, but you have to do the same thing. You have to do the same thing on the shear catalog as on the fiducial catalog, otherwise. You can't, do
What fiducial catalog? I'm confused.
the unshared catalog.
Well,
You do the same thing on all 5 catalogs, but it has to be the metadetection catalogs. You can't use the standard DM catalogs, the main ones they make for, you know, general astrophysics and science with shear.
So
in
the
metadetection.
But
Just for the catalog where you care about the shears. For the lenses, you can do all the fancy stuff you want. That none of this applies to the lenses.
So the way I think of it is that there's going to have to be 2 completely different sets of photo Z estimates. There's the ones in the object catalog, there's the ones in the shear object catalog, and you can use the object catalog ones for lens samples or galaxy clustering or whatever else. But if you're doing for source lensing source samples, you have to use the shear object catalog photo Zs.
Yeah, so in DES, there are literally 2 separate photo Z pipelines. There were in Y3, there are in Y6. One for the lenses, one for the photo Zs. And they were different, and now basically in Y6, they're probably going to be basically the same. But that's neither here nor there.
But you mean literally like you train them on different sets of things because they're going to have different ensembles that they're looking at, and the priors are going to be different. And
I don't know if they need to be that different. But they need to be able to work with different quantities coming out of the catalogs because the catalog quantities are not quite going to be the same.
Yeah, and there's only one photo Z code I know of that actually uses training. Everything else is done as a likelihood inference on ensembles of objects because it's easier to characterize and it's very accurate. So, you know, we just don't think about individual photo Zs anymore for cosmic shear. It's just not a useful quantity.
Oh, it's okay. It's a little unrelated, but can I ask?
but I mean, what about the clustering people? Do they think about individual photo Zs for cluster membership? And what do you do with the fact that these are different things?
Cluster, like galaxy cluster membership, or like angular clustering on the sky? Well, if you're using RedMapper constructs its own internal red sequence photo Z. So that is, and Eli's sitting in the room, so he can tell you how that works. So people do that, but that's all on the lens side essentially, right? Not on the source side.
Oh, sorry, it wasn't quite photo Z related, but I also wanted to clarify, can you not then apply a blendedness cut to the objects in the shear catalog?
You can apply any cut that you can compute in the metadetection pipeline. So that's, you know, so if you can compute some quantity and it's computed on all the images and the detections properly, and it's not totally crazy discontinuous, I'll just add some caveats there that you actually need to be able to get the gradient out of it, then you're good to go. In practice, all of the tests that Aaron and I have done, we've never applied a blendedness cut, and the shear inference is fine. And so there is going to be blending, and the real question that is, you know, non-trivial is where do you put all of the blending effects? So if you adopt metadetection as your shear measurement, and you don't deal with any blending, and they all end up in your photo Z distribution. And so that's a lot of the work that DES is done in order to characterize how essentially the shear measurements we have respond as a function of redshift, and blending plays into that. If you make a blendedness cut, it'll shift you know, those distributions likely around. We don't use any blendedness cuts in DES. Other surveys do, of course. Everybody does things a little differently. But you do have to deal with it. It's just, it goes in different places.
So because we can run things inside the metadetect loop that aren't actually used to measure the shear, there's nothing technically wrong with us running Scarlet as long as the Scarlet isn't used to run the ellipticities. And then you could get a blendedness out of that. I don't want to run Scarlet itself because I don't want to do it 6 times. But we could find other cheaper ways to get it, something like a blendedness, if we thought that was going to be useful.
So, yeah. The caveat there is that if you run it on the zero shear catalog and you want to use it to compute the response, you need it on all the other ones.
Yep.
So you have to be careful. It's not 100, but you'd have to test. So we know that if we deblend objects and measure their shapes, it's wrong. We haven't tested if you deblend them and get a blendedness quantity and then just use that as a cut, if that also makes the shear wrong. I don't actually know. So that would be something you'd want to test in a simulation before you actually did it. Sorry, I think I interrupted somebody. My apologies.
So this is sort of a follow-up on that question. This is a little more general, just to make sure I understand. So I think the statement is that you can make whatever cut you want, that it has to be in the metadetect loop, and you can never make any cut later. So for example, we could never define a gold sample or change our definition of what the gold sample is after the fact using that shear catalog. We have to decide ahead of time.
If you do it derived from quantities from the shear catalog, you're also safe.
Yeah, it's fine. It's fine to cut and signal to noise later. You just can't match to the main catalog and cut and signal
Okay,
to noise.
so as long as we
You have
use
to-
things that are in
yeah.
the columns of the shear catalog,
Precisely.
that's totally fine.
Yeah.
Mhm.
But we can never go back to the original information that made that column. That's the general rule. Okay.
Yeah, I mean, you could go measure objects again, but you'd have to go back to the actual metatech images, you know, PSF deconvolved, sheared, the whole thing, and then make more measurements. It'd be very expensive.
But that's actually not what I've been hearing, because, Jim said we can run algorithms and Matt said, yeah, but some of these algorithms
Yeah.
don't work. So it's
That's
not,
true.
you can grab columns in the catalog. It's
yes.
entirely possible that there could be columns in the catalog that you shouldn't be using.
Yes, so using the shear object catalog for undercuts is necessary but not sufficient.
Right. So how do we communicate? So how do we avoid the situation that a bunch of graduate students in the P of Z group go off and come up with like really clever things to do with P of Zs and then get told that was cute, but we're never going to use this because you violated, these particular constraints.
But can you clarify first the rule? So I'm hearing two different things.
Okay.
So if I use something that's in the columns of the object shear catalog, you're saying there are some situations where you shouldn't even do that? What are those situations?
Yeah,
There-
let me say it this way. In the shear catalog, there could be two kinds of columns. There could be shear safe columns and not shear safe columns. And the point that we're making is that you can make cuts on the shear safe ones when you're trying to do cosmic shear, but you won't be able to make cuts on the not shear safe ones when you're trying to do cosmic shear. We don't have any not shear safe ones right now, but we could in the future.
Ideally, we wouldn't put any shear unsafe columns in there, but we might decide we're going to put this in here, even if we don't know that it's shear safe, so someone can balance and see whether it is, after we've run it. Well, I don't think there's any value to having a known to be shear unsafe column in the shear catalog, but there might be, we don't know how shear safe this is columns in that catalog.
So I apologize. I've been trying to multitask. Maybe you discussed this, but at one point we were thinking of having at least two catalogs with one with really good seeing and one just everything.
Yeah.
Where does that stand?
I don't think that's been part of the plans that we've been working towards for a long time. There was some language about building best seeing coads, but they were never supposed to be retained. So it was sort of like DM will build these and then it will forget they built these, and the science user will never see them. It never made any sense in the documents we wrote like down at FDR. And so we fixed that by like sort of removing mention of them because they didn't make any sense. I'm somewhat skeptical of the idea that you get a lot by co-adding best seeing coads, by making best seeing coads, because it's really a combination of seeing and signal noise you want. And we're not going to, the deep coads are not going to include the very worst seeing. Like if it actually makes the signal noise of the coad go down, we're not going to include it. And so I think that's just where we're at in terms of what we are scoped to do. There are coad algorithms that like formally avoid this problem entirely with a coad weights essentially that include doing it in the Fourier domain, so you can deal with the differences in the PSFs. We're not going to do that for DR1 because it's too late and we don't want to mess up the validation that's already happened. But I really would like to do that for later data releases, and then I can formally tell people, no, you don't need best seeing coads. These are the best possible coads. I really want to get to that point, just not for DR1. And Eric had a good point we never got back to about how we train the community to not shoot themselves in the foot. And that is
I can speak for the desk, but I won't speak for any groups outside of the desk. So basically, this is a communication thing that needs to happen in the desk and hasn't happened yet, which is if we're going to use this for shear, which is the current plan, then the kinds of photo Z techniques we can use is very much limited and has to fall in certain categories of things that have been done in some previous surveys, but may not be sort of what is being done mainstream in the desk right now, or might be. I don't actually know enough about the desk photo Z effort to say either way. But yeah, this is definitely a communication thing that has to happen within the desk. But outside the desk, people can find me. I don't know. It's going to be a lot harder.
But even in DESC, there's a whole lot of cosmology that will not be done on the shear object table. There's a whole lot of cosmology that will be done on the main object table, and the kinds of photos
Exactly.
we're working on are also still very useful for that.
And I mean, basically what you've what you've made clear is that there's got to be a photo Z use case matrix of what you're allowed to do and what you're not allowed to do. And,
Yeah.
that has to be maintained and communicated. So that, we don't end up with unfortunate situations where, people put a lot of effort into something that's never going to be used. But okay, that's clear. We can move on.
I guess, could I ask though, related to that, is there a plan for how to put together all the quantities that should be in the metadetect catalog so that they cover sort of all the different possible use cases that would be possible with shear safe quantities?
So I would love to drive that sort of informally through DESC. I think I'm certainly open to hearing that there are other science collaborations that want input into that, but like since the weak lensing science collaboration got absorbed into DESC years ago, I've sort of assumed that all the people who care about what's in that catalog are in DESC. And if DESC can tell us what columns they want, I mean, they're also have the people who are writing the code to generate those columns. That's the easiest way for me to handle it. Certainly those columns are not set in stone by any means right now.
It might also be helpful to talk to other surveys. And hopefully they have some presence in DESC, but in HSC, I feel like we had unexpected cuts that we ended up applying. And so kind of talking through experience of all the different odd cases that came up might be helpful.
Yeah, I think a lot of that'll get hashed out in the first couple of years when people say, oh, I want to do my science. Wait, I can't do science. And so it'll get fixed in fairly short order, because if you need something and it's easy to measure and we haven't, we'll just add it. So
For sure. And even the algorithms that are in the DM pipeline, the DM version of Metadetection now are outdated compared to what we're using in DES. So they already need an update because we've changed stuff. So this is an ongoing sort of thing that we have to do as a group.
As a non-DES person, I'm very aware that the state of the art right now is in DES. And a lot of this is sort of like, well, when DES year 6 comes out, then I'll know what we're going to do or have a better starting point. And right now I'm sort of like, yeah, we'll wait to see what they do first.
So I'm just curious for DES, are there any implications about, as you said, some cosmology doesn't use the shear catalog, but we combine pieces of cosmology together to do cosmological inference, right? Like even in something like 3x2 point or whatever, you include clusters. And so are there any, so that means the selection effects for those samples won't be the same and they may have different depths. Yeah. Yeah, and then they must have different depths. Are there any, I'm just curious, are there any special things that you have to do that would be different than other things that you would normally have to worry about if we're using different catalogs for the different pieces?
I mean, we lenses and sources are always different catalogs, and you want your lenses to be shallower than your sources so that they're lensing the sources, right? So all that stuff is necessarily true just to make the science even make sense.
Okay.
The place where it seems like it might get tangled is in intrinsic alignments, because those are the only places where you start to care about like your galaxy wallpaper as galaxies rather than as wallpaper. But it's still mostly, I think, lenses that get
yeah, we do look at the magnification effects. I don't know, Matt, if you want to talk about that, but like, is there any kind of selection-y things where we do the inverse, like treat the lenses as shears?
Oh, I don't know of any, but yeah, we will be directly simulating magnification effects through all these data products and DES to make sure we get the coefficients right in the model.
Yeah,
for sure.
I suspect because that's already a second order effect that like this would
Yeah.
then be like a third order perturbation to something that's already a small correction. So I think it's probably not a problem.
Yeah, I just want to emphasize again, because I think a lot of this looks very familiar to people who work in DES now, but it looks totally foreign to many people in the room. The key thing to remember here is that the devil you know is better than the devil you don't. And that's roughly the phrase. But by discretizing into these cells, it gets you a lot of things that you can just compute over the cell and know exactly what they are. And so you have to have a strategy for how you're going to handle all of that stuff down the road in order to account for it, but at least you know what you did, so that then down the road, you can figure out how to account for it. And that's how you'll get to an analysis where the likelihood is actually correct. So at least that's been the approach that we've taken, and that I think is useful.
All right, I'm not seeing any more hands. We've still got 10 more left if people want to talk, but we can also just go to coffee early, I think. Last call. All right. Thank you all for coming.
Thanks,
Bye, everybody.
Thanks, Matt.
and especially thanks to those who are online as well.
You're welcome.